Right, so question 4, we've got our spheres colliding again, our favourite. It is possible to do some extra work you don't need on this question, and if you look at my handwritten solutions, you'll see some of the extra stuff I worked out I didn't actually need. So it is important to have a clear diagram. So using the information, I'm going to set up some things here. So I'm going to label my angle there as theta, so that's going to be theta for both of those, so the angle between the line of centres and the direction they are moving. Coefficient of restitution is a sixth. Now, having got theta, I can then use the information in the question, so you see this is 1.6r, to work out some information about theta. So there's 1.6r. If I label this theta, so I'm looking at this one here that I'll label in red, that one that I've labelled in red. So this is point B, and this is the centre of A. Okay. So B, A. Right, well, what do we know? Well, A to B is going from A across there, which is going to be one radius, and then across to B, which is going to be another radius. So that's going to be 2r. And from that, I can work out the other side of the triangle is 1.2r. And then from that, you can use this triangle to work out a lot of information about the angle. So I can work out that sine of the angle is 0.8 and cos of the angle is 0.6 if you just use sine is opposite over hypotenuse and cos is adjacent over hypotenuse. Okay, so that's going to be quite useful. We do also need a clear picture on this. So this, A is moving with speed u, B is moving with speed 2u. A has a mass of 3m, B has a mass of 2m. So this is my at the time of collision picture. And then I need to define what's going to happen. So after the collision. So again, this is still going to be A and this is going to be B. And what I'm going to do afterwards is split my components of the velocity into two. So along the line of centres and perpendicular to the line of centres, and that's just going to perhaps make it easier for me to deal with this afterwards without having too many angles going on. So I'm going to say that's VA along the line, that's VB, because what you can actually work out while you're doing this is perpendicular to the line of centre, so the impulse acts along the line of centre. As you imagine them colliding, so that's where the impulse is going to act. So perpendicular, there's going to be no change in the component of the speed. Now you don't actually need this for the question, but you can work it out, and you can work out that for A, this is going to be u sine theta, which is 0.8u. For B, you're going to have 2u sine theta, so that's going to be 1.6u. Okay? Now you didn't actually need those in the question, but you might like to put them in your diagram, work them out for completeness. Okay? Right. So, however, we are trying to find the magnitude of the impulse. So the impulse acts along the line of centres, which is why we never need to know what's going on perpendicular to line of centres. So along the line of centres, I can first of all look at conservation of linear momentum. So to start with, I've got particle A has a mass of 3m. So if I'm trying to resolve along the line of centres, I want that blue arrow there, you can see that's adjacent to my angle, so that's going to be u cos theta. Now B is moving in the opposite direction, so I'm going to say the positive direction for momentum is that way, which one diagram helps you. So B is going to have momentum 2m times 2u cos theta. So afterwards, now A is moving in a negative direction, so that's 3mVA, V is moving in a positive direction to MVB. And if you put in all your numbers, so you see I've got cos theta, worked out cos theta was 0.6 up here, you can simplify all that down. So negative 0.6 u is negative 3 times VA plus 2 times VB. So that's going to be my first equation. The other thing we always look at, and this is going to be along the line of centres, is our coefficient of restitution, which in this case is a sixth. Now they're now moving apart, which means the speed of separation is VA plus VB, and when they're going towards each other, they are literally going towards each other. So the speed of approach is done by adding the two components of speed in that direction as well. So again, I've got cos theta, I can substitute in for that. So this is going to be 3u cos theta, so I can do 3u cos theta, which is going to be 1.8 theta, times a sixth is VA plus VB, which is going to give me 0.3u is VA plus VB, which is going to be my second equation. Now I want to solve these two simultaneously, so I'm going to need to do something to do that, so I'm going to multiply my second equation by 2. Then I can bring down my first equation. That was equation 1. And now, if I subtract those two, the velocity of b's will cancel out. So I can then solve them simultaneously and get velocity A, velocity B. Okay, again, you don't actually need both of those because I'm trying to find just the impulse. So I actually need one of those, but it doesn't take long just to solve for both. And it also means you could then check your answer if you wanted to. So our impulse is going to be my change in momentum. I'm going to look at particle B. Okay, so if I look at particle B, its mass was 2m. Its final velocity is in this direction. It's what I've called VB. Subtract the initial velocity. Now, just velocity speed along that line was going in the opposite direction, so that's going to be negative relatively. And then I just put in the numbers I've got. So afterwards, it had its component of the velocity was 0.06 u. Initially, we can sub in cos theta, so cos theta was 0.6. And then simplify that. 2.52 m.